percent of the total. Conformations and stereochemistry. Predominantly from chapter 3 is about 5 to 8%. And approximately 80% would be the actions. There will be very little on physical properties. Now, what does reactions really mean? You have learned 4 different types of reactions and some analogous ones. So the reactions really involve not only making one organic compound change to another one, but also how does the reaction proceed? Because in many cases there are competitions, and we haven't discussed competition, but we'll get to that much later. But at this point, you should be able to identify them based on what's used. And so let's go over that. What we have seen is 4 different types of reactions: SN1, SN2, E1, and E2. So the fundamental difference between the S reactions are essentially substitution, right? And E stands for elimination. That part is easy. But then SN1 and E1, they both involve a carbocation formation. They go through a distinct carbocation formation as an intermediate. And SN2 and E2 are one-state process. Also in the rate expression, the SN1 and E1 involves only the substrate in the rate expression. The substrate could be an alcohol, it could be an alkyl halide, but they go through essentially no other reagents are involved in the rate expression, which is the slowest step in the process. And in the case of SN2 and E2, the rate involves not only the substrate, but also either a nucleophile or a base. Now, in some cases, the base and nucleophile could be the same thing. And why one would proceed better than other? Okay, that's something that we'll discuss in chapter 8. But even at this point, you should know that the order of basicity and the order of nucleophilicity are different. They are 2 completely different tables. One, AJ, for example, could be a good nucleophile and a poor base. Another one could be a good base and a poor nucleophile. And there are also a third type where you have good nucleophile, good base. Those are all to be discussed later. But at this time, at least you will be able to differentiate them. And I'll give you some examples of that. If this reaction we are carrying out, okay, the agent is particularly important. In both cases, it involves the formation of a carbocation. But the first one that I indicated, sulfuric acid with heat, the negative part of the molecule, which is HSO4 minus, is an extremely poor nucleophile. And therefore, this is an example where the reaction will predominantly go through an E1 mechanism. So this is an example where you are going to get the elimination product. HBr, which is also a strong acid, except that it at the same time generates Br minus, which is a good nucleophile. Therefore, the ability of this reaction to go through SN2 pathway will generate a completely different product. So this is an example of SN1 process. Even though it started with the same reagent. Okay. And both of them involve the intermediate formation of a carbocation, which is really the this is the intermediate in both cases. And when there is an absence of a nucleophile, it goes through the E1 pathway. When there is a reasonably good nucleophile present, it will go through the SN1 pathway. Now, if we change the substrate and can carry out the same reaction, it also can change the whole pattern. So now, rather than using a tertiary butyl alcohol, let's use just propanol. Now in this case, the substrate is changed now from a tertiary cation, this is tertiary, we changed it to a primary. And the consequence of that is the generation of a primary carbocation is extremely high energy that does not usually form, and therefore it needs to be assisted by another reagent. Now in the case of sulfuric acid, what happens is that you may get small number of water molecules that can still catalyze the reaction. So the first step in the process is formation of a protonated species where the proton has been transferred to the oxygen. Now, because it cannot break the bond between the carbon and oxygen, what happens is one of the hydrogen can be abstracted by water, small amount of water that is present there, and it carries out both the reaction of removing the hydrogen and eliminating the water molecule from this to form the corresponding So this is now, we change the mechanism from E1 to E2 because the rate expression would include also the presence of the water molecule which is taking part in this removal of the hydrogen. So this is now an E2 process. And likewise, in this case, the HBr can do the similar things except that now it's being attacked by Br minus, although this reaction is not very good, but it can still take place. The same intermediate is being formed, but this is now attacked by Br minus. Giving you an SN2 product. So that's kind of some of the differences that we see in this type of reaction. the E2 reaction can also take place under the conditions of dehydrohalogenation. The dehydrohalogenation essentially means you remove hydrogen and halogen from adjacent carbons. And that can be carried out in the presence of a strong base. So this is an example of E2 elimination, where you may have if you remember, we mentioned that the strong bases are typically alkoxides. Okay. So sodium or potassium with oxygen and R group. The R group could be methyl, ethyl, anything, any of that groups. And normally we use the corresponding alcohol to make them. You add sodium to ethanol, that would make ethoxide. If you use sodium to tertiary butanol, that would make tertiary butoxide and so forth. So, and you use the corresponding alcohol as a solvent. And this is really a positively charged species, whereas the oxygen is a negatively charged species. That's the one that attacks and essentially removes one of the hydrogen from the beta carbon. So this is alpha, this is beta, and pulls out the proton and kicks out the bromine in one state. That's why this is the E2 mechanism, where now, typically in organic reaction, even though I have written ROH and NABR, etc., of course they are formed, but most of the time organic reactions, you start with a substrate which is organic starting material. We use an arrow, we use the reagents, and use the final product here. And of course, it has other things, but the arrow indicates that we really are focusing on the main substance that we want to prepare. So it's the organic reagent, and frequently we just omit all the others. Okay. That doesn't mean that that doesn't exist, but our focus is on the substrate that going to the final product, which is the organic compound that is being generated. And that's why it's different from general chemistry, where this document is very important. It's also important here, but most of the time we kind of ignore that because the type of reaction depends on what substrate you start with and what reagents you use, what condition solvents you use as well. Now, the E2 reaction, on the other hand, you have a question? Oh, yeah.
What's the ROH underneath the arrow E?
Okay, ROH is the alcohol. You need a solvent to carry out the reaction. And typically for this type of reaction, we use the same alcohol. Like if you use sodium ethoxide, you want to use ethanol as a solvent because ethanol will be one of the products generated, and using the same solvent makes it easier.
That's just the product, like the inorganic product that's made from whatever's above the arrow?
Right, so okay, it could be, this R is essentially what if you use methoxide, you use methanol, right? So that would be methyl group here. And then also the product that is generated from here, that's why you don't show that, because that would be dissolved in solvent, which is the same in this case. And like example, another example is that you use a strong base like NH2. And we typically use ammonia for that solvent. because ammonia would be one of the products that would be generated, and you just use that. So we consider on the base, which is NH2 minus. All right, and of course there are some variations of these type of reagents. Often, as I mentioned in this case, this reaction doesn't go very well because it's primary. And so if you want to make a bromide, an easier reagent to use is PBr3. And if you want to make chloride, you use thionyl chloride. So these reagents are particularly useful because they give better yield of the bromides and chlorides from even primary or methyl alcohols. So if you use, for example, so it can be very easily converted to the bromide. And typically, often with this reagent, sometimes the catalyst helps the reaction to go faster. And typically for this, we use a weak base such as pyridine for this reaction. Likewise, you use thionyl chloride, that would be converting this to the corresponding chloride. And again, pyridine is the catalyst used for this. Now, the mechanism of these reactions are also very straightforward in the sense that if you have thionyl chloride, SOCl2, the structure actually is, let me rewrite the structure, SO, Cl, Cl, and sulfur has 2 electrons as well. As you know, sulfur ions the octet rule. So this is the reagent that we use. And the way this reaction proceeds is again a nucleophilic attack from the oxygen of the alcohol, which attacks the sulfur and displaces one of the chlorine. So mechanistically then, this generates 2O, H, positively charged, S. All right, and one of the function of pyridine is actually removal of this proton. So the pyridine in the next step pyridine is just like benzene with one nitrogen replacing a CH. So the pyridine picks up this proton, neutralizing the charge. So So this is generated, and now the chlorine can attack, and I'm not showing all the electrons. You have 8 electrons in the chlorine, Cl minus. So it attacks this and displaces that and kicks out the other chlorine, essentially generating the corresponding chloride. Plus SO2 plus pyridinium So this is kind of a follow through the reaction of how this reaction proceeds. Now, something that we did not describe in detail and something that is also very critical is to understand the energetics of these reactions. And I have gone through a couple times, but let me go one more time just to emphasize that. In the very first reaction that we described, the E1SN1 pathway, remember this reaction. It's very critical to understand this reaction proceeds, and we already described what the intermediate is and how this reaction proceeds in terms of the rate expression. The rate is, this is the slowest step in the process, and then that gives rise to the product depending on U1 or SN1 pathway. So they both have the same intermediate. So how this reaction goes is energetically is that you protonate, and I'm writing R in order to make it simpler, ROH plus the acid, giving you ROH positively charged. That's it provided the proton. And therefore, when you look at any energetics like that, you know the transition state, which is the top of the hill, is intermediate between these two structures. So how do we write that? The way we write is that ROH remains exactly like the way we had. Now, a new bond that is forming with another hydrogen. So we use a dot, 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 H. The charges now are coming from the proton, which has some positive charge, and some positive charge already transferred to the oxygen. So this is the transition state structure. So this is TS1. Now in the next step, it goes to the carbocation where it breaks the bond between the R and the O. And that is the redeterminate state, going to the product, which is R plus, H2O, and whatever else is left. We're showing them. Again, you can draw the structure indicating that the breaking of the bond between R and oxygen. So we use dot, 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 oxygen. And the charges are also transferred. Partially in this case positive charge. The oxygen still maintains some positive charge. And the two bonds with hydrogen are intact. So this is the TS2 structure. And according to the Hammond postulate, it also tells you that this structure is actually closer to this. This one is almost broken because this is closer than this one, where the bond is completely intact. So that gives you an idea of how far this reaction actually already went. So this is the transition state 2. That goes to the final product. And the final product would depend on what is the acid. If the acid also generates a new nucleophile like Br minus, Cl minus, anything, then it is an SN2. Otherwise, it goes slightly higher energy and goes to here. That would be the elimination pathway. So this is the elimination pathway where you generate a double bond, and here it would be RX, whatever X is. Okay. So both of them go through the same intermediate, but then one goes to the alkene, the other one goes to the substitution product. So that's kind of the summary of the energetics, and obviously this is the ready to use because the energy of activation is highest here. Okay. This one is small, and this one is also small. All right? No, this is actually both. This is SN1, and this is E1. SN2 is completely different. SN2 is when you change the R group to primary, then this goes up, but in one state it goes to the prime. SN2 and E2. All right, so let me go over the practicing step. All right, so the first problem is all nomenclature. As you can see, you already know that. And the way we do the numbering in this case is you can do from right to left or left to right. The priority of the alkene groups and the halogens are the same. So ideally, I put it 1, 2, 3, 4, 5, 6. Okay, because from the other direction, you will get 2 position has a chlorine, but then 3rd position has nothing to do with 4th position here. So 2 and 4 compared to 2 and 3 is better. Understand that rationale, right? Okay. So this one therefore is 5 chloro and 2,3 dimethyl. 2,3 dimethyl hexane. This one you have to start numbering. The double bonds get a higher priority. Therefore, you cannot start from the chlorine. Therefore, you got to do 1, 2, and 3. You cannot do 1 and 2 here because you have to make sure that the double bond is 1, 2 and not 1, 2, 6 or 1. So therefore, it's 3 chloro, 1. This is 6, 1, 2, 3, 4, 5, 6, 7. Empty. Yeah. Even in other cases, it's 1, 2. We did 3 chloro, 1 empty. Yes, otherwise, right. Otherwise, it could have been in another position. Though in this case, 1 heptene is needed. Because you may have multiple other substituents there. What? Right, of course, cycle. Absolutely. This is now the cyclohexane ring system. This is a tertiary butyl group. You can also call it 1,1-dimethyl ethyl. And this is the alcohol, therefore that gets high ranking. And if we call it cyclohexanol, we also need to indicate the relationship between them. And 1,4 relationship, 1 axial, 1 equatorial is what? Cis or trans?
Cis.
Right. So this is cis. 1, 1. 1, 2, 3, 4. 4, 1, 1, dimethyl, ethyl, cyclohexanol. This one is again, this is outside the ring, and therefore you have to consider this as the longest chain. And this is really a derivative of 2-propanol. So 2-cyclohexyl, 2-propanol, or 2-cyclohexyl, propan, 2-ol. And for this type of compound, you have Z and E. You can draw the structure first and then figure out the A and Z of those. So like this is 4-ethyl 3-iodo 3-heptene. So you need to draw 1, 2, 3, 4, 5, 6, 7. So 4-ethyl 3-iodo 3-heptene. So 1, 2, 3. 3-iodo. 4-ethyl. Okay, so we have done that. Now let's figure out if the one that I have drawn is Z or E. If not, then you can switch them. So in this case, this is higher than the ethyl group. And in this case, this is higher. So what I have drawn is actually Z structure. Because the larger groups are on the same side. The E3-methyl-3-pentene 1-ol is also drawn the same way. So 1-ol, so draw OH, pentane, so 5 carbon, 1, 2, 3, 4, 5. 3-methyl, 3-pentane, 1, 2, 3-methyl, 3-penton, 1-ol. All right, so now in this case again, we look at the higher group is this one with respect to the double bond, and this is lower. This one is lower. This is actually higher. This is H is lower. So higher and lower on the same side that we're seeing. If not, then you switch them. Just rewrite that structure. And when you draw 6-member ring system to chair form, then you can draw them in the following way. That you have, start with the largest group, CH2OH, give that one as equatorial, draw CH2OH. Next we go to the OH, which is trans relationship. If this is equatorial, then the trans is also going to be equatorial. Go to the next one, that's again trans relationship, so other would be equatorial. This two also is trans, so this should be equatorial as well. But final one, this one is 6, therefore it must be axial. And this is the most stable structure. If not, then you can always flip that one. Okay? Whether the two structures in each of the pair represent a institutional isomer, different conformation, or stereoisomer. So the first one, this pair, as you can see, that if we flip this molecule, the methyl becomes equatorial and the ethyl becomes axial. And therefore, that's what is shown in the other structure. Therefore, there are two different conformations. Different conformations. Now, the same thing is true here, except for the fact that you have a second ring system, which makes this one unable to actually flip. Because there are two axial bonds, they cannot be made equatorial. And therefore, this is locked. And once it's locked, then they are no longer conformers, they become stereoisomers. So this is equatorial, this is axial, and therefore these are stereoisomers. But if you didn't have a second ring, then they would be conformers. These two are identical. If you redraw them, you'll see the same structure, same name, but two different conformations. So they are different conformations. And in this case, you will come up with two different names because this one, chlorine is in one position. This 1, 2, and 4. And in this case, chlorine is in two positions. So they are actually constitutional isomers. The next question is very straightforward. You need to identify the secondary alcohol. So you have to focus on the carbon to which the OH group is attached. Ignore everything else. So this is the carbon to which is attached. This one is the carbon which is now tertiary. This one is primary. This one is secondary. And this one is not even alcohol. So therefore, secondary alcohol, this one is secondary, two carbons. This is tertiary, primary, secondary. Those are the two answers. The same way you can do the other carbocation. Most stable carbocation would be tertiary. And therefore, this is primary, this is tertiary, and these two are secondary. So these questions are really, it takes only a few seconds to do it, as long as you recognize that. Okay, and as you can see that these are reactions, and there will be questions like that, very similar to this one, where you need to identify the main organic product, and you can ignore all the inorganic compounds that are generated. So in this case, now this is, what kind of reaction is this? You should be able to recognize now. How this is coming. What? Give me a letter and a number. What letter and number associates this reaction? E2. Right. Because we use a strong base, alkoxide. The substrate is secondary. This is going to undergo an E2 reaction. And this is the alpha carbon. This is beta. This is beta. The two beta carbons. So both of them have hydrogen, therefore two products are possible. Okay, so this beta carbon gives you double one here. This beta carbon gives you double one here. Which one is major? The first one, right? This is according to Seitz. So this is major, and that's very critical. You need to actually indicate which one is a major product, otherwise you'll lose points.
Yeah, so it only versus draw the principal organic product, you only draw the major product, that's sufficient, or you need to draw?
Well, you need to draw, like in this case, you should draw both of them and indicate which one is the major. The major product is, it must be indicated, yeah. If you just write the products, then you will lose points. Oh, in some cases, it is acceptable to write only the major product, unless I ask for that specifically. Now this one goes through again carbocation, a strong acid. There is no good nucleophile. So what kind of reaction is this supposed to go through? Most likely E1 process. So you generate a cation, and what happens is that you can generate another cation that is more stable than that. So this is the initial product, and then it can do a metal transfer, giving rise to this cation. Okay. And this is going to give you mainly this product. But also from this one, you can get this product, which is minor. So this is major. The next reaction is, of course, only one product. Yes.
Sorry, if you did go, if you were trying to show the minor product,
Yeah.
you could draw the double bond.
You can get a product here also, but that would be extremely minor. Less than 3%. Okay. So this is now is a fairly straightforward reaction, 3 ethyl groups attached, and therefore again you are going through this process, but typically this is a tertiary carbocation followed by the chlorine group attacked here, and therefore this is the major product. EPR3, we indicated that again, focus on the alcohol group, and that everything else remains intact. CH2Br. And this is tyrene chloride. Again, just make sure that you write all the carbons 1, 2, 3, 4, 5, 6, 7. G4, 6, 7. CS.
It's not no reaction. What kind of we expect to see that every process reaction?
No reaction?
Yeah.
Well, yeah, there are. Most of the ones that we discussed so far will have generate some product. Okay, so don't worry about that at this point. Okay, and this is really the energy diagram that we talked about a few minutes ago. And you need to figure out what that really means. There are different letters associated with different stages. So A is of course the starting material, which is this. And the final product is D. Right? And so all the other intermediates, if we recognize this reaction is going through typically an E1 pathway, because we get an elimination product according to the equation 1. And so the structure that is drawn here, you need to actually concentrate on that and see what happens is that you have a dotted line between carbon and oxygen, and the positive charge is distributed